So the discriminant value is basically the b square minus 4ac is called discriminant of this auxiliary equation. And now based on the value of the discriminant, we have three cases. So let's discuss each case one by one. So case 1, where b square minus 4ac is greater than 0. Okay, so in this case, obviously when b square minus 4ac is 0, you have two roots given by something like this, where I'm calling b square minus 4ac as d. So these are the two roots. Okay, and so that's why there are two roots, and therefore the solution is r1t is one solution, and you have two solution, the second solution y2. So y is y1 of t e power r1t, and y is equal to y2 e power r2t. Okay, so these are your solutions of differential equation, the second order differential equation. Now we using the important two facts which I described before for linear differential equation. So I described two facts, important two facts. The first fact was, if I know two solutions, then any linear combination of the solutions will be also a solution. So combining y1 and y2 in this way, I can say that a e r1t plus b r2t is also a solution, is a general solution for any choice of a and b. So this is the case. So this is the general solution where r1 and r2 is given by these roots for this differential equation. Now case 2, what happens when b square minus 4ac is 0? Okay, so when b square minus 4ac is 0, d is 0, discriminant is 0, roots are equal, and roots are equal to minus b by 2a. Okay, and let these two be general r. So we know that y is equal to r power t will be a solution. Okay, so now here when y is equal to e power rt is a solution. Now let's say y r power t u power t is also a solution. Now this is one assumption. Okay, now assuming that y, because we got one solution, but it has to have a two thing, two solutions. So y is equal to e power rt ut. Let's substitute, let's that this be the given solution and substitute it back in the given rt. So y dash will be e power rt u dash t plus e power rt into r u of t. So just we apply the chain rule. So this will become e power rt u dash t plus r u of t. This is y dash. Similarly, y double dash will be in the same way e power rt. Just differentiating it two times. It will be u double t plus 2 ur t plus r square u of t. So this is just when you differentiate y dash again one more time, apply the chain rule, you will get this. Now substituting all that in the given differential equation, which is something like this, if I substitute all that, I'll be getting something like this. E power rt is a common, rule 0. Now we know that this is 0. Okay, we know this is 0, and e power rt cannot be 0, we know that. So the only option is that 2ar, and this is also 0 because we know that r is minus b by 2a. Okay, r is minus b by 2a. So the only thing that makes this entire equation to be 0 is that u double dash t has to be 0, because constants a can't be 0, in general. Okay, so u dash t is 0, so u of t is basically something like this. Okay, u of t is something like this. So we can say that y is equal to a plus bt. Now substituting this here, here, substituting this, we can say that y a plus bt e power rt is the general solution. Is the general solution. So this we started from this given thing and found out a general solution for a case where roots are equal. Okay, so let's discuss case 3, where say b square minus 4ac is negative. So when b square minus 4ac is negative, obviously the discriminant is less than 0, and then you have the complex root. So I can write b square minus 4ac inside to be negative, and I can, so let me express this form by some k plus I plus or minus I omega. So I am basically, r will be a complex number and it is represented in this way. So obviously your solution, one solution will be something like this, and your another solution will be something like this. So these are two independent solutions, but are not real valued. Okay, and what we are looking is, we are looking for a real valued solution. So let's find, so what we do is we find two real valued functions that are solutions of star. So star is basically the ar square plus br plus c I'm calling star. So what we do is, see now, if I just use these roots, these are not real valued, these are complex, but I need to find real valued functions which are the solutions of the auxiliary equation. So what I'll do is I'll combine y star t and y2 star t in order to form a real solution. So how I'll combine is y1t, I'm just calling y1 star t by 2 plus y2 star t by 2. So basically I'm just in this way I can just add the real part, and in order to get the other solution I'm just combining these two in such a way that I get real valued functions. So I'm just combining in this way. So this will give you y, if I add these two, so this will give you y e power kt cos omega t. So this is nothing but you have to just write in the form of e power I theta I can write. So this I can write e power kt. Okay, remember one thing, that this is complete O and this is complete O. Okay, so you have to simplify it. I mean this, the way you simplify it is e power kt into e power I omega t I can write. Okay, plus e power kt into e power minus I omega t by 2 is something which it becomes, and then e power kt by 2 is constant. Now e power I omega t using, so this is basically the exponential form, so I can write cos omega t plus I sin omega t, and this also I can write cos omega t minus I sin omega t. So I sin omega t terms will cancel, and inside you will get 2 cos omega t, which will directly lead to this. So this is my one function. Similarly, if I try to find out this 1 by 2i and e power star it, again I can write in this way. So it will be e power kt, okay, into e power I omega t by 2 minus e power kt to e power I omega t by 2. So same thing, e power I omega t, again I have to write cos omega t plus I sin omega t. So that on simplification, let's simplify. Okay, e power kt is common, by 2 I'll get is cos omega t plus I sin omega t minus cos omega t minus I sin omega t. Okay, anyhow y2 was minus, so minus it will become plus. Okay, so this I'll be getting 2i cos omega t, and this will be basically your 2, yeah, so 2i sin omega t, you will get 2i sin omega t. Yeah, there is no 2 here, sorry about this 2. Okay, so you'll get 2i, and here you have 2i, and obviously here you will get 2i, so this will give us to e power kt sin omega t. Okay, this will give rise to e power kt sin omega t. Okay, so basically you have, so the general solution, I can write the general equation, I can say that okay, this let me just write it down clearly. E power kt sin omega t is the general solution. Okay, so general equation, I can say that it's basically a combination of these two, y1t and y2t. So I can write a e power kt cos omega t plus b e power kt sin omega t, and this you can just simplify e power kt common, cos a cos omega t plus b sin omega t. Okay, so this is case 3 general solution. I mean general solution, it's better to call general solution rather than equation. Okay, so 3 cases. First, if you have the real roots, the general solutions are a e1 e r1t plus b e r2t. Basically all the theorem 1 we are using, the important fact 1. If you have equal roots, then it is a plus b t into e power rt, where r is the common equal root. Case 3, if it is complex, just find out r, and if it comes out to be k plus or minus I omega, then the solution is e power kt a plus a cos omega t plus b sin omega. So there are 3 cases depending on the equation. So this is just 3 different cases for homogeneous second order linear differential equation. So whatever we have derived, let's see some examples in order to solve just the second order linear differential equation homogeneous case. So let's solve some examples on whatever we have discussed, and then later we'll extend that to higher order linear differential equations. So example 1, find out the general solution of y double dash plus y dash minus 2y is equal to 0. Okay, so in order to compare with this form, comparing with this, we get a as 1, b as 1, c as minus 2. So obviously the auxiliary equation, the quadratic auxiliary equation, will be r square plus r minus 2 is equal to 0, and the roots we can just find out by that formula, minus b plus or minus b square minus 2ac by 2a. So this will be minus 1 plus or minus 1 minus 4 1 minus 2 by 2. So this is minus 1 plus or minus 3 by 2, which is if I add, I'll get 3 1 comma minus 2. So these are real, and the roots are real and not equal. So the general solution we have derived is e power r1t plus b r2t. So the general solution is e power r1 is 1 plus b e power minus 2t, r2 is 2. Okay, so this is how I can just write, this is the solution. Okay, so let's take another example. Example 2, where I have y dash plus 6y dash plus 9y is equal to 0. See, remember we are dealing linear differential equations of second order with constant coefficients, okay, and the homogeneous type. That is important. So the auxiliary equation for this will be r square plus 6r plus 9 is equal to 0, and this I can just readily write in this form, or you can use the quadratic formula. So the roots are minus 3 and minus 3, so roots are equal. Yeah, roots basically are real and equal, okay. So minus 3, so I can just use the second case which I derived, a plus bt into e power rt. So this is nothing but a plus bt per minus 3t. So this is an example for the real. Now let's take another example where I have something like this, y double dash plus 4y dash plus 13y is equal to 0. Okay, so let's solve this case, y double dash plus 4y dash plus 13y is equal to 0. So the auxiliary equation will be r square plus 4r plus 13 is equal to 0, and this let's use the quadratic formula. Again, it will be b square, which is 4 square minus 4ac by 2 into 1 2a. So I got minus 4 plus or minus 16 minus 52 by 2. 16 minus 52 is basically 36, and plus 36 uh, it is minus 36, and so I can write basically minus 6 and then by 2. So this together can be written as minus 2 plus or minus 3. So basically two complex roots. So when you have complex roots, okay, so remember k is minus 2 here and omega was 3. So I can write the general solution e power kt, I mean k e power kt a cos omega t plus b sin omega t was the general solution. So e power minus 2t, and I can write a cos 3t plus b sin 3t. So this is the third case where you have the roots to be complex. Okay, so let's discuss another example. Solve the initial value problem. Y double dash plus 2y dash plus 2y is equal to 0, given that y of 0 is equal to 2 and y dash of 0 is equal to 3. So basically this is an initial value problem where the value of y and y double dash at x equal to 0 is given. uh, Remember that this is minus 3, sorry, it's not 3, it's minus 3. Okay, so same thing, this is a second order linear DE homogeneous. So whatever we have discussed we can readily use. So just forming the auxiliary equation, you can get r square plus 2r plus 2 is equal to 0, and this will give rise to minus 2 plus or minus b square minus 4ac by 2. So this, if I simplify, I'll get minus 1 plus or minus I. So again, two complex roots, okay, so comparing it, putting in this form, k is equal to minus 1 and omega is equal to 1. So we know the general solution for this case is e power kt a cos omega t plus b sin omega t. Okay, so e power minus t a cos omega, omega is 1, so a cos t plus b sin t, a cos t plus b sin t. So this is the general solution. But now we are in order to find out arbitrary constants, the way we need to I mean why we need to find out arbitrary constant, because already the initial value is given. So y of 0 is 2 implies, so substituting t0, so e power minus 0 a cos 0 plus b sin 0 is equal to 2. So e power 0 is 1, cos 0 is 1, so a is 2. So that we readily obtain. Now y dash t is equal to how much? Well, this is something you need to differentiate. E power minus t, applying the chain rule. So a cos t is minus sin t is cos t, and then keeping a cos t plus b sin t same, e power minus t, you have to differentiate e power minus t into minus 1. Okay, so now substitute t is equal to 0, you will get e power 0, then minus a sin 0 plus b cos 0 plus a cos 0 plus b sin 0 e power minus 0 into minus 1. This value is minus 3. Okay, so this is a sin 0 is 0, so we'll get b here, and here a cos 0 is 1, b sin 0 is 0, we'll get minus is equal to minus 3. But a we got as 2, so it will be minus 3 plus a, which is 2, b is minus 1. Okay, so that's why now the equation will be e power minus 3. A is substituting all a in this equation. This is the general solution. A cos t minus sin t. So you sin t, yeah, omega is not there. So this is like 2 e power minus t cos t minus e power minus t sin t. Okay, so this is the solution for that given initial value problem. So now till now we have discussed the second order homogeneous linear differential equation. Now extending the same concept to higher order. Remember what was common in all this was the coefficients of the linear differential equations were all constants. It was not function of x. So now extending whatever we have studied for the second order linear differential equation with constant coefficients, homogeneous case, to higher order. So extending this to higher order. And remember, this is the homogeneous case. Okay, so in general with constant coefficients the equation looks like something like this, and the nth derivative plus k1, the n minus 1 derivative, I mean you can express in this form. Okay, where k1 to kn are all constants. Now in most of this literature, maths literature, and the differential equation, in order to avoid cumbersome writing, what is denoted is d is denoted by d by dx, d square is denoted by d square by dx square, and so on. So d power n will be d by dx power n. Okay, the nth derivative, yeah, nth order derivative. Okay, so this equation will basically become d power n plus k1, I can write d power n minus 1, so on, plus constant kn into y is equal to 0. That is what I can write. Okay, now whatever we studied for the second order differential case, we substituted y is equal to rt into this, and this was the, in order for this to be the solution, okay, the auxiliary equation has to be 0. So similarly here, there it was quadratic equation, here the auxiliary equation will be basically putting r in this, right? So it will be r power n plus k1 rn minus 1, so on, kn is equal to 0. So this was your auxiliary equation, and so for y is equal to e power rt to be the solution of this nth order linear homogeneous case, this has to go to 0. So this obviously will have n roots, and let the roots be in this form. Suppose you are able to factorize this way. So now again the roots are m1 m2 and till nth root. Okay, so now similar to your the quadratic case, we are not doing anything magic here. We are just extending the quadratic, the second order linear differential equation to this case. Okay, so now let's say two roots are real. I mean the roots are I mean all the roots are real and unequal and different. I mean unequal is like different. So in that case, we can say that the general solution, so obviously then your y r1t, y is equal to er2t, y is equal to er3t. So these are different solutions, and general solution will be basically a linear combination of all of these n independent solutions. So you have n independent solutions which are something like this. These are all independent solutions. Okay, so the general case will be a linear combination of n independent solutions. So I can write y as c e1 m x. I mean this is, I mean so I mean instead of t you can put x also. I have used t here. You can put x also depending on what is your independent variable. Okay, so y is equal to c m1x plus c2 m2x plus so on, the basically the number of, so basically the number of roots. Okay, so this is the general solution for case 1 when the roots are real and different. Now case 2, when two roots are equal, say any of the two roots are equal, so then just using the quadratic philosophy, I mean the second order philosophy, there if two roots are equal we used to write a plus bt into e power m e power rt. Now, similarly extending this here we can write c1x plus c2 e power mx, and then from now on the c3 m3x, because m1 is equal to m2 is equal to m, so that's why we have kept, and the remaining is similar, remaining doesn't change. Okay, and now if three roots are equal, can happen, all the roots are real here, roots are real, only thing is that two roots are equal, so three roots are equal, so in that case you can write c1x square plus c2x just in the same manner e power mx. So here you can say three roots are equal means I can write this way, plus your c4 m4x plus c5 e m5x plus so on. So this is how when three roots are equal. Okay, now coming to case, this was case 2, sorry, and this was case 3. Now case 3 is when roots are complex, two roots are complex. Okay, because complex roots appear in pair. So say you have one pair, I mean what it means is one pair of imaginary roots. Okay, if you have that case, then the solution will be basically, if you have constant, so m1 will be basically let's say alpha plus I beta, and m2 is alpha minus I beta. So in that case I can write, remember that e power k plus I omega, similar to that you can write e power kt, so e power alpha x plus your c1 is again constant cos beta x plus c2, there we had a and b in the second uh, order term, and the remaining is similar. Okay, so this is just extending the second order linear differential equation homogeneous case to nth order, or any order, I mean higher than 2, any order higher than 2, let it be general n. So we are extending the second order philosophy to the nth order philosophy for linear homogeneous differential equation with constant coefficients, because it's only the constant coefficient is there in the syllabus. Okay, so now let's solve some problems in order to have this higher order linear differential equations, the homogeneous case. Let's solve some problems. Okay, so let's solve one example. The first example, y the fourth derivative minus 16y is equal to 0, and the second b bit is the fifth order derivative minus 2y is y3. Okay, so there are two example problems. Let's solve step by step. So this is the equation. So I can write d power 4 minus 16 of y is equal to 0, where d denotes basically d by dx, right? Okay, so now the auxiliary equation for this will be r power 4 minus 16 is equal to 0, and this means that I can write in this way. So r square plus 4 to r square minus 4 is equal to 0, and therefore the roots are, for this the roots are plus or minus 2, and for this the roots are plus or minus 2i. So basically you have minus 2, 2, minus 2i, 2i. So these are the roots. Okay, these are the roots. So two equal roots and two complex roots, I mean two not equal, real and different, and then one pair of complex. Okay, so one pair of complex. So I can write for these real and different, I can write c e power minus 2t plus c e power 2t, and for complex roots I can write e power. Now, here just putting in alpha plus or minus beta form, alpha is 0 and beta is 2, right? In this form, comparing this complex roots in this format to, okay, beta is 2. So I can write e power alpha x was the thing, and you had c3 cos beta x plus c4 sin beta x. So in that form, alpha is 0, so this will be 0. Okay, c3 is constant, cos beta is cos 2x plus c4 sin 2x. Okay, so this I can write finally as something like this. E power 0 is 1, so c3 cos 2x plus c4 sin 2x. So this is the solution. Remember that there are just note that there are 4 arbitrary constants because the order is 4. Okay, now coming to the b bit. Okay, y minus 2 y4 plus y is equal to, okay, coming to this case, well, here the auxiliary equation will become r power 5 minus 2 r power 4 plus r cube is equal to 0, because you're in terms of d differential operator, d is basically called as a differential operator. I can write something like this. The entire differential equation can be written this. So this has to be the auxiliary thing. Okay, so now how do I solve? R cube is common, I can take out common. Okay, so r has so this, let me just again simplify this. I can write r minus 1 whole square, basically r square plus 1 minus 2r is equal to 0. So what are the roots? Roots are r is 0, 0, 0 here, and then 1 and then 1. So two sets of equal root. So this is one set of equal root, and this is another set of equal root. Okay, so I can write, for this set I can write c1 plus c2h plus c3h square for this set, and for this set I can write c4 so that's the thing. Equal. Okay, okay, let me just write down correctly. Okay, so this is e power. Okay, let me just rewrite it again. So y is equal to, this is one root, so I can write c1 plus c2 x plus c3 x square into e power rt, and then so e power 0t basically, then c4 plus c5t, and then e power, this is r1 is 0 here, and r2 is 1. So just comparing that, so this will become c1 plus c2h, this is h, sorry, don't let me not confuse with t. Okay, c1h plus c2h plus c3h square e power 0t, which is 1, so r1 is 0, and then c4 plus c5t e power 1t, so e power t. So this is the general solution. Sorry, again I'm confused with t, so let it be in terms of x only. So the general solution is c1 plus c2x plus c3x square plus c4 e power x plus c5x e power x. So this is the general solution. So let me write down here clearly, c1 plus c2 x plus c3 x square plus c4 e power x plus c5 x e power x. So this is the general solution for this case. Okay, so basically we have seen in this section we have seen the second order differential equation linear type and a homogeneous case, and then we have seen how to extend that second, or we have seen basically how to solve the second order linear differential homogeneous equation, and then based on that philosophy we have extended that to a higher order homogeneous linear differential equation, and we have solved a couple of examples for each case. So now let's see how to solve non-homogeneous higher order linear differential equation, because if you have the right hand term, then what happens? Okay, so one thing has to be clear here, that we now till now we have used only the fact 1 of linear differential equation, basically the theorem 1, which says that if you have any two solutions y1x and y2x, the general solution is the linear combination of basically the linear combination of the independent solutions. So that is the general solution. And now for non-homogeneous case, we'll use basically the theorem, the fact 2 or the theorem 2 statement, which says that if you know the solution of a non-homogeneous case, okay, an independent solution y2x, and if you have the corresponding solution for the homogeneous case, then the general solution for the non-homogeneous case will be basically the sum of these two. So we'll see that fact, basically the complementary function, the particular integral. So now let's solve the non-homogeneous linear case in the coming section.